students, so we have just finished up learning about physical properties, chemical properties, but what are these properties of? What is this matter you speak of? What is it made of? Well, I'm going to tell you it's made of atoms, and I'm sure you've heard that before, but we're going to go back to a time where they had no idea what they were actually made of. They could have been made of anything, way back when. So let's go back to the time of Democritus. So the atom. There was evidence of it in India as early as 600 BC. Believed as early as 400 BC, though. Democritus called something atoms. He was actually a philosopher. He had no concrete evidence, but he knew there was stuff out there, and that stuff was made of atoms. And he thought it is indivisible. This is the smallest level of stuff that could exist. Atoms are it. They're the basis of everything. Everything's made of atoms. Everything else is space. He also thought atoms were indestructible. Again, he was just kind of guessing, but he was theorizing. And that's what that happy-looking dude looks like. He actually was called the laughing philosopher. He doesn't look like it, but he was. His ideas were disagreed with at the time. Aristotle, Plato, they thought he was full of it. They thought everything was made of elements like air and water, and that really held weight for a long time until other people came along, like our good friend Dalton. But things had to happen before 1808, before Dalton could make up his theory, and let's talk about what those things were. People needed to discover these. First was the law of definite proportions. This is something that you probably know about, and we've talked a little bit about, but we're going to put it in concrete terms here. And it's just that compounds, like water, are always made of the same proportions of elements. Ethylene glycol looks like this guy here. It's always 2 carbons, 6 hydrogens, and 2 oxygens. It's never going to not be in that ratio. Even if you have a lot of it, it's always 51.56 oxygen by weight, 38.70 carbon by weight, and 9.74% hydrogen by weight. No matter how much you have or how little you have, that's how much you have by weight. Sodium chloride, something you're a little more familiar with. That is NaCl, and that is our table salt friend. It is 60.66% chlorine and 39.44% sodium. That's how it always is. Everything is definitely proportioned like that, whether you have a lot or a little. Law of conservation of mass. This one makes a lot of sense. It's what goes into a reaction always equals what comes out of the reaction. If you don't have great equipment, you can't really prove this. Now we can. We could show if we react calcium chloride with sodium sulfate, it's going to make calcium sulfate solid plus sodium chloride in solution. We know that. And if we start with 300.23 grams, we're going to get 300.23 grams as long as we have a closed system, like shown here. Again, law of conservation of mass. And then probably the most confusing of these three is the law of multiple proportions. But it's less confusing than it really seems like. Basically, it's that elements that form multiple compounds. So hydrogen and oxygen, you put them together, you can either get water or you can get hydrogen peroxide. One of these is vital for life. One of these is going to kill us super dead. They both occur when you combine hydrogen and oxygen together. And the law of multiple proportions is basically just saying that the ratio of the masses of the second element will always come out as a ratio of small whole numbers. It's not going to be anything crazy. You're not going to get 1.26 to 1 oxygen. It's always going to be one whole number. It's going to be 2 to 1 by mass. Again, by mass. So our boy Dalton, who looks very serious here, but also kind of like a boss, sitting there in his chair. In 1808, he's a school teacher. He's an English school teacher, but he's a smart dude. English teachers are smart, but this guy's a scientifically smart dude. And he used the concepts of Greek atomos. That's what Democritus was calling them. The law of definite proportions that we just learned about, the law of conservation of mass, and the law of multiple proportions to come up with his good ideas. He came up with the idea that elements are always made of one kind of atom. Compounds have two or more kinds of atoms. This sounds familiar because we talked about it last unit. And only whole atoms can form compounds. It's always going to be H2O, not H1.2 or 8 or H.60. It's always H2O. And he also thought atoms, they're spherical and they're very, very small. So he came up with his 5 principles. And the last 3 are the ones that are the most important for us to think about, because the first 2 were actually disproven. And we're going to talk more about that soon. But Dalton's 5 principles. First of all, he thought all matter is made of tiny little particles called atoms that cannot be subdivided, created, or destroyed. Again, they can't be created or destroyed, but they can be subdivided. All atoms of an element have identical physical and chemical properties. Now, let's think physical and chemical properties. Let's just think about water. Water can be a solid. Water can be a liquid. Water can be a gas. It's all got chemical properties that are the same, but those physical properties, they don't always have to be the same. And now we move on to the good ones. Different types of elements are made of different types of atoms. Okay, that's good. That makes sense. Atoms combine in simple whole number ratios, H2O. Got it. And in chemical reactions, atoms are combined, separated, or rearranged, but they're never created, changed, or destroyed. Again, law of conservation of mass fits into his 5 principles. It sounds great. And it's important because it explains how all the chemical data that currently existed in 1808. He had this nice model of atoms, and he thought they kind of looked like this. We kind of have a little more modern idea of atoms now, but in 1808 this is revolutionary. The technology doesn't exist, and he's making leaps and bounds. And he gives us proportions for molecules. NO2 is always 1 nitrogen, 2 oxygens. N2O, 2 nitrogen, 1 oxygen. Nitrogen monoxide, 1 nitrogen, 1 oxygen. Again, though, was he exactly right? No, that's the beauty of science, is even if you're not 100% right, you can revise your ideas, and sometimes it takes a long time to do that. The first 2 principles were not always true, but again, that's fine. He had evidence. He used all the evidence that he could to come up with those ideas. And not all of his elements were really true elements. Lime, soda, baking soda. That's sodium bicarbonate. That's sodium, hydrogen, carbon, and oxygen. He thinks these things are exactly one thing, but again, he didn't have the technology to really observe all of these things. However, he gave us some great ideas. We're not going to throw out all of his theory. In fact, he was so important that they named units after him. That's a big deal in the scientific field. If you get a unit named after you, you should hang that on your refrigerator. It's a big deal. But it was revised. We're going to show you how it was revised. It was revised. Because our boy J.J. Thomson comes along. This mustachioed man was an English physicist, and he really wasn't studying the atom. He was just interested in electricity. I don't blame the guy. Electricity is very interesting, especially at his time. And he was playing around with something called a CRT, a cathode ray tube. It's what he's got in the picture right to his right there. I guess it's his left, our right. You can see it there, and it's a neat little thingamajig. It's got a cathode on the end and an anode in the middle. The cathode's got the negative part there, and it's got a little stand. It's got a vacuum tube. Look at that neat little cathode ray tube. What did he do with it? Why do we care? It looks complicated and dumb. Well, it's not. Come on. Let's look at it. It's called a cathode ray tube because it's hooked up to the cathode end of the tube. If you hook it up wrong, you hook it up to the anode, it doesn't work. It's a vacuum, so the only thing inside of it is things coming from the cathode, the negative end. And really, at the time, they hooked it up. They saw this neat beam. They thought, oh, look, it's probably light, but maybe it's particles. And so they shoot, they turn it on, and they see this nice green beam. And then they bring a magnet in, and it starts to bend towards the magnet. When they flip the magnet around, it bends the opposite way. So they're thinking, wait a second, I can bring magnets up to lights, and lights don't do this. This is not a light. This has got to be particles, because it's bent by those magnets. So the ray has to have a charge, as it's affected by the two different opposite ends. And it's attracted to the positive, and we know negatives are attracted to positives. Positives are not attracted to positives. They repel positives. So we know it's got to be negative. Thomson, our boy, he discovers the electron. But he's also saying they have to have mass. We know they've got mass. It's not much mass now, but at the time we didn't know that. But Thomson, he discovers the electron. That's exciting. However, if there's this little thing called an electron, wait a second. Dalton's model can't be right. Dalton says that atoms, they're the smallest thing. They can't be divided up. But there's these electrons. This can't work. So it's got to be much, much, much smaller than an atom in order to shoot like it does. So it's got to be smaller. This changes atomic theory. We have to add this. And he postulates if there's negative electrons, there's got to be a positive in there to balance it out. And he comes up with something called the Plum pudding model. If you look at plum pudding, you could see it's got all these little dots in here. It looks reasonably delicious, but it's got this big outer part and then all these little dots inside. And that's what he thinks for his model. He starts with Dalton's model. Thinks it's hard, it's spherical, it's small. However, he adds that atoms can be broken down. They can be broken down into big parts, big positive parts, and it's broken down in smaller parts, these little negative parts. And that's what he believes. And this is where I'm going to leave you, because this is going to change. But this is just the first part. I don't want to throw too much at you at one time. So that's the first video. You learned a little bit about history. You learned that sometimes science can change. And that's a good thing. As you get new evidence, you have to revise those theories. You have to make them better. But I really hope that you learned something.